He's talking about carbon graphite and carbon diamond. Before we proceed with a follow-up to what you did yesterday in discussion class. Diamond, much harder, much more durable, of much greater structural integrity than carbon graphite. Yet the carbon-carbon covalent bonds in graphite are stronger than those in diamond. So how can the first part of what I said be true? But the structural integrity of diamond being far greater than the structural integrity of graphite. The difference lies in comparing the strengths of covalent bonds, which we've done, to the overall strength of the bulk material. Because in the bulk material diamond model, every carbon atom in the sample in a crystal of diamond is part of a three-dimensional covalent network of bonds, a network of covalent bonds. Every carbon atom in this lattice is covalently connected to other carbon atoms. There are no other type. There's no other type of bond interaction between and among carbon atoms in a diamond lattice other than covalent bonds. Now, in 2045, when you talked about bonds, were you reminded about how covalent bond strengths compare to intermolecular forces of attraction? What are the three types of intermolecular forces of attraction? Strongest type of hydrogen bonding. Strongest type is hydrogen bonding. No hydrogen bonding here.
Dispersion.
And dipole-dipole. No dipole-dipole forces here. And van der Waals forces, also called London dispersion forces. An attraction force exhibited by anything that's material. All forms of matter show London dispersion forces, which are in the main proportional to what property of the matter? What? Consider the halogen elements: fluorine, chlorine, bromine, iodine. Under normal laboratory conditions, do you know how the phases of samples of these elements compare? Fluorine, chlorine, bromine, iodine. How do the phases of these materials under normal lab conditions compare? Fluorine, gas. Chlorine, gas, but derived from a liquid of a higher boiling point than fluorine. Bromine, liquid. Iodine. You know anything about molecular iodine in 45 laboratory, the solutions experiment? Did you? Yeah. You're damn right. What phase was it? I got to get this administration to understand that this partnership stuff is a waste of time. There's no learning going on. Well, we'll forget that for now. Okay? Why is the iodine solid? Bromine liquid. The other two samples, gases. London forces are much stronger than the iodine, because London forces in the main are proportional to what property of the material? What? What? Formula mass. And iodine atoms are far more massive than bromine atoms, etc. Okay? Put another way, iodine molecules are far more massive than bromine molecules. So intermolecular forces of attraction among and between iodine molecules are the strongest of the halogens, discounting radioactive astatine. Back to carbon, diamond, and graphite. All the atoms are sp3. Diamond, all the atoms are covalently connected to nearest neighbor carbon atoms. The only type of interaction between and among the carbon atoms in the diamond lattice is the covalent bond. In 2045, regarding what I just discussed with you, did they make mention of how the strength of a covalent bond on average compares to the strength of the strongest type of intermolecular attraction force, which is hydrogen bonding? About 100 times stronger, if not more. Hey, covalent bonds are strong. Now then, graphite. We noted yesterday, each carbon atom in the graphite lattice is covalently connected to 3 nearest neighbor carbon atoms, not 4. Each carbon atom in the graphite lattice is sp2 hybridized, not sp3. But each carbon atom in the graphite lattice, like each carbon atom in the diamond lattice, is in a covalent network of 4 bonds. sp2. So what you have for each carbon atom in the graphite lattice, which is hybridized sp2, is resonance. There really are no double bonds. They're all covalent bonds between the carbon atoms, which are shorter and stronger than a CC single bond, but longer and weaker than an actual CC double bond. You learn this about resonance, I should hope and think. The only picture I can draw of this is this. But there is no double bond here, just like there are no single bonds. What's the carbon-carbon bond order in the graphite lattice? 4/3, 1 1/3. When resonance applies, when resonance is a property of the material, you take each of the resonance stabilized bonds for a given atom. Here, 4. One, 2, 3, 4 bonds for this atom, our reference atom. And divide by the number of bond sites under consideration. That's the way you get bond order. 4 bonds divided by 3 bond sites, 4/3. There's a covalent bond between carbon atoms which has a 4/3 bond order, stronger than a covalent bond which has a bond order of 1? You're daggone right. However, these covalent bonds that are part and parcel of the graphite lattice only interconnect the carbon atoms to each other, which share the property of being in the same plane. All these atoms. Let me hold the model this way. You see how this plane of atoms is separated from this intermediate plane of atoms by a much longer distance? What does this much longer distance simulate? What kind of bonding? What kind of bonding? London dispersion forces. Very weak. The weakest type of intermolecular attraction force. So when you take a sample of graphite, like that which is part of your pencil, and shove it across the paper, and leave behind a smear of graphite, now known as your notes. Have you broken any carbon-carbon covalent bonds in doing this? Not any, none at all. What have you broken? You've broken these weak London forces and torn planes of carbon atoms from adjacent planes of carbon atoms. That's what you've done. Upshot. the overall lattice for graphite is of lower structural integrity. It's looser, so to speak, than the diamond lattice. That gives this lattice, the graphite lattice, a higher entropy or a lower entropy than the diamond lattice. Which has the higher entropy? Graphite lattice, we've got these weak London forces between the planes of atoms, or diamond lattice, where all the atoms are connected to each other by covalent bonds, nothing else. Which has the higher entropy? Graphite lattice. But which has the stronger bonds? Graphite lattice. How about that? That's why from a delta H standpoint, this is more stable, and from an entropy standpoint, this is thermodynamically preferred. Look again at the thermodynamic properties data table. Look at it right now. Carbon, graphite, carbon, diamond. And as you look at this, realize, when you take and consider from a thermodynamic standpoint the formation of a mole of the most stable allotrope of an element from a mole of the most stable allotrope of the element, is there any change in energy? None. Any change in entropy? None. You're considering making a mole of stuff from itself. No change in thermodynamic property function for that kind of change. So those materials have delta H sub F super 0 values and delta G sub F super 0 values of 0. You see that in the table for carbon graphite? You looking at the table? But if I'm going to consider forming diamond from graphite, after having recognized that the covalent bonds between and among the carbon atoms in graphite are stronger, then when I convert graphite to diamond, is this an exo or endo transformation? I'm going from stronger bonds to weaker bonds. Is that exo or endo? Exo or endo? Stronger bonds to weaker bonds. Exo or endo? If you want to weaken bonds, do you have to put in energy, or does this transformation take place naturally? If you want to weaken bonds, if you want to weaken the intermolecular attraction forces among and between water molecules and ice and get it to become liquid, do you have to put in energy, or does this happen all by itself and give off energy? Do you have to put in energy to get water to ice cubes to melt? Finally, we got there. So if I'm going to weaken bonds, which is what I'm doing when I go from carbon graphite to carbon diamond, the transformation requires the input of energy. This transformation is guaranteed endo. So when you look in this data table, in the delta H sub F super 0 column for carbon diamond, you're going to see a positive number. Do you see it? That's the amount of thermal energy you have to input to the graphite lattice to bring about this bond weakening, because that's what you're doing when you change the daggone graphite to the diamond. How about that? Now look at the entropy values. Because from an overall bulk sample standpoint, the diamond lattice is much more durable, of much greater structural integrity. Much more tightly bound are the atoms from an overall standpoint to each other. None of these London forces in the diamond lattice. So when you look at the entropy values, which one has the higher entropy? Graphite does, doesn't it? Look at the data. Do you see this? How about that? Because one of the main points of this conversation was to get you to start to understand what the heck this data in this table means. Statement. There's more chemistry in the thermodynamic properties data table than any other single collection of data. Because this stuff tells you about structural integrity of materials, about bond strengths. Hey, that's what chemistry is all about. So, as a follow-up to yesterday, since again all the gatherings didn't make the same degree of progress. After we get further into thermodynamic considerations, which is what chapter 21 in the notes is about, because what we've done so far is to try to make sure you know what standard state means, you know what the sub F means, you know what the information in this thermodynamic properties data table means. How do we get a relationship, quantitative relationship, between thermodynamic property functions and the most important thermodynamic state of material? What is this most important thermodynamic state of material to which I refer? Equilibrium. Well, the arithmetic that leads to this relationship is offered in the notes. It's again something I choose not at all to hold you responsible for. I don't care about the derivation at this stage of the game, but you can do it. Some general chemistry books, in fact, offer this. That, I would say, is to their credit rather than their discredit. But it requires a rather sophisticated understanding of the thermodynamic property functions of gases. And I really don't take the time to do that. I'm far more interested in getting at the details of solution chemistry, particularly solution chemistry that takes place in, guess what, solvent? Water. Because, damn it, we live in a water-solvent life system. There's no argument that all these things which are commonly considered in general chemistry class to general chemistry class to general chemistry class and by general chemistry textbooks are important. But the word general means anything goes. And chemistry is a huge discipline. It's absurd and ridiculous to think that we can consider all the important parts of chemistry in the first year. You can't consider all the important parts of chemistry if you lived 1,000,000 lifetimes. You get these people who are trying to sell you these learning programs that you deal with on the computer. Mastering chemistry. That's a real hoot. I don't know anybody who ever lived who's mastered chemistry. It's too much. It's too difficult. It's too overwhelming. And they're going to have you master chemistry. What they're going to do is program you to solve their stupid problems. And I'm not having none of those junky programs in my class. Not now, not ever. These people that try to sell that stuff, they usually talk to me once. They'll come back after that. Because I tell them the same thing I just told you. I says, all you bastards want to do is make money. You don't give a damn about the educational process at all. You get the hell out of here. Quick! Woo! Away they go. And I said, you can tell anybody else I said that. And if you don't want to tell them, I'll tell them. You just get out of here. You're not interested in advancing the cause of education. In fact, these people that come around don't know anything about chemistry. That's the best part of it. All these people are trying to sell me educational products for chemistry, and they themselves don't know anything about chemistry. What a lie! I don't put up with that junk. And I wish everybody would share my opinion, my attitude, but that's a hope. In any case, solution chemistry. To get at solution chemistry from a thermodynamic standpoint, we have to define a reference point. Many of you heard about this yesterday. I'm curious if you heard about this in 2045. My bet is you didn't. This is another big gripe I have with the 2045 class as it is presently conducted. You do all this Hess's law stuff, all this calorimetry stuff, and you don't do anything with water solution chemistry, which is the only damn chemistry that is pursuable by our first year students in the laboratory. You're not doing anything to relate what you're doing in class to what they are capable of doing in the laboratory. Let alone the fact that water solution chemistry is the most important period. And they don't do it. You know why they don't do it? Because it's tough. You see what we've been through to get at the acid-base stuff? It's not easy, is it? It's detailed. It's difficult. But it is indeed pursuable if you think about it. We have not asked you to engage in any consideration from an arithmetic standpoint, which is beyond first-year high school algebra. How about that? So there's really no math limitation on your ability to get at this stuff. The limitation, if there is some, comes from the ability of the character who stands in front of you and talks to you about this stuff. Because if that person doesn't understand the stuff, there's no way this stuff is going to get across to you. And that is the big gripe I have with these general chemistry textbooks, because none of them do a reasonable job with solution chemistry. None. And as I said, in my opinion, water solution chemistry is the most important. That's what we ought to go after. If nothing else, it'll make you aware of why chemistry is important. I mean, hell, what are we? 70% water, for starters? Okay, back to this reference point. The formation of our good old H plus AQ, whatever the hell that is, at this pH. Now notice this is 1.000 molar, right? If we take pH to an infinite number of significant figures. That's defined as 0. Forming the hydrated proton, or put another way, forming a water solution of pH 0.0000 forever. Which means this reaction. Are we not forming H plus from the most stable allotropic version of its component element in the required quantity? Yes. So, we consider this reaction and say this corresponds to delta G sub F super 0 for this H plus AQ, and set all these thermodynamic properties for this reaction and for the material itself equal to 0 by definition. That gives us a reference point. Because, notice this is a half reaction, right? It's a reaction which by itself cannot be run. I can't go get a bottle of electrons and shove them into a half a mole of hydrogen. So I define this purposely as 0. And then I make a bunch of measurements of other half reactions relative to this, which thereby allows me to get thermodynamic property information for all other solution species. And we'll talk much more about this in the next chapter, electrochemistry. This also results in the fact that forming the true hydrated proton, which as I see it is hydronium ion, has no change in thermodynamic property function for this reaction. Because for this thing, all these thermodynamic properties are 0. So this thing can't have any thermodynamic property function value other than 0. I mean, if nothing else, the true hydrated proton is at the minimum hydronium ion. We'll take it as hydronium ion, and in the next chapter, at the end of this chapter, we'll give you a good reason why hydronium ion is arguably the correct formula for the hydrated proton. So, since delta H, delta S, delta G for this reaction is 0, it must be true that the standard free energy of formation of the water molecule and the standard free energy of formation of the hydronium ion itself are equal to each other. Right. If I made this by adding an H plus to this, which has got a bunch of zeros for these thermodynamic properties, then delta G sub F super 0 for this is equal to delta G sub F super 0 for this. Now you got to be careful about this, because I don't want you to think that adding H plus to ammonia will give you the ammonia, which gives you the ammonium ion. I don't want you to think that the ammonium ion has thermodynamic property function values which are the same as ammonia itself. That's not true. So we'll take this also as a defined statement. For this reaction and this reaction alone, in addition to this reaction, all these thermodynamic property functions are 0. So, as we said, by running a different half reaction in conjunction with this, a reference half reaction, we can get delta G0R for the total reaction, which gives a delta G0R for the other half reaction, because by definition, delta G0R for that part of the puzzle is 0. So what I asked the folks to do yesterday in discussion class, so I'll ask you folks right now, how many of you saw this yesterday? I mean, you know, you're going to see it now. I'm just curious if you saw it yesterday. This is also in the notes. If you took time to read all of chapter 20, I won't ask for a show of hands. Look at this half reaction. It's a half reaction. Any reaction which has got electrons as reactants or products, that's a half reaction. A reaction which by itself cannot be run. But look at this particular half reaction. Half a mole of hydrogen vapor phase, most stable allotropic version. Half a mole of diatomic oxygen vapor phase, most stable allotropic version. Adding an electron to the product of this reaction in the presence of water gives us, guess what? Our hydroxide ion. So if I can get delta G0 for this reaction, what I have in fact obtained is delta G sub F super 0 for the hydroxide ion. The standard free energy of formation of the hydroxide ion. And so I can also get the delta standard enthalpy of formation of the hydroxide ion, as well as the standard entropy of formation of the hydroxide ion. How can we get that? You know how to do that. This is what you did in 2045 in the chapter on thermochemistry. You applied Hess's law. Have we used Hess's law already this term? Did we learn how to take an equilibrium reaction for which the equilibrium constant is not supplied and recognize what fundamental equilibria that overall equilibrium reaction was composed of? Didn't we do that in chapter 19? We applied Hess's law. That's what we did. Because these thermodynamic property functions are known as state functions. Remember that from 2045? What's that mean, state function? Path independent. Far different than kinetic dependency. If I own a trucking firm and you work for me and I tell you to take a truckload of stuff from here in Gainesville to Jacksonville, delta H0, delta G0, delta S0 for this transformation is the difference in energy and entropy between Gainesville and Jacksonville. It doesn't make any damn difference how you get there. You know the most direct route. You go out on Waldo Road and 301 and zip over to Jacksonville on I-10. Okay? But hey, maybe you're in a happy mood. Or maybe you're a boy truck driver and your girlfriend's in Miami. So you take my truck from Gainesville, you drive to Miami. And then after you spend some time at the beach and drink some beer and have some fun, a couple days later you get back in the truck and you drive north on 95 and you get to Jacksonville. You call me up and say, hey, I made it. And I said, thermodynamically you're great, but kinetically you just flunked. Because you cost me one hell of a lot of gasoline and took way too long. Even the thermodynamic part doesn't care about the too long, doesn't care about the path. The state function aspect. So, take a look. Hydrogen reacts with oxygen to make water liquid. We know about this. You can run this reaction, measure delta G under standard state conditions. You get delta G sub F super 0 for water liquid, which is minus 237.1 kilojoules. How about this reaction? 2 moles of water liquid giving hydronium ion 1 mole thereof and hydroxide ion 1 mole thereof. Hey, you know this reaction. This is Kw in reverse, isn't it? From an equilibrium constant standpoint. So if I give you that fundamental relationship to use, which I wrote up there, that delta G0 for a reaction is minus 2.3 R times the temperature in Kelvin times the log of the equilibrium constant. And you express R in energy units joules. And you're also going to multiply this by 10 to minus 3 kilojoules per joule. you get delta G0 for this reaction. The delta G0 value for this reaction. Is it plus or minus? Delta G0 for this reaction. Is it a plus number or minus number? Is this thermodynamically spontaneous under standard state conditions? No. Is this thermodynamically spontaneous under standard state conditions? That means, does water in a glass of water naturally react with itself to make hydronium ion at a concentration greater than 1 molar, and in the same solution, hydroxide ion at a concentration greater than 1 molar? Does that happen in a beaker of water? Hell no. So delta G0 for this thing is what? Plus or minus? Plus, you betcha. And then our define reaction hydronium ion. Up there we got water plus H plus makes this. We're going to look at this in the other direction because delta G0 is 0 by definition, and H plus electron making a half a mole of hydrogen. So we're looking at this define reference point reaction in the opposite direction. Who cares? Delta G0 is still 0. Now what's the point of all of this? Hess's law. Add this, to this, to this, to this, and what do we get? We get this. So Hess's law says, since these thermodynamic property functions are state functions, if I add this reaction to this reaction to this reaction to this half reaction, I get this half reaction. Which means if I take the delta G0 value for this and add it to this and add it to this and add it to this, I get delta G0 for this, which means I got delta G sub F super 0 for the hydroxide ion. This is 0, this is 0. You don't know how to get this. Did I write it down? I don't know, maybe. Let's see. Yeah, 79.8 kilojoules. So these are 2 zeros. So all you do to get delta G sub F super 0 for hydroxide ion after we've done this work is to add this number to this number. So you get about minus 160. It's minus 157.3 for this. Kilojoules for forming a mole of hydroxide ion under standard state conditions. Well, that shows you how to get this stuff. Okay? Now then, we've laid the basis for tying together thermodynamic property functions for a reaction with equilibrium. And the final arithmetic connection is that relationship up there. Delta G0 is minus 2.3 RT log K. Oh, I wrote it again here. Okay. So now, we're going to look at this reaction. Okay? We're going to consider an experiment. An experiment which, after we discuss, with good fortune you will realize, although we can discuss this experiment, we can talk about this experiment, we can't do it. What are these fancy pieces of artwork representing? Piston inside a cylinder. Each at NLC. This one contains 1 mole N2O4 gas. This one contains 2 mole NO2 gas. So if we expect these gases to behave ideally, and they will for the most part, then we can calculate the internal volumes if we're at NLC. 1 mole of N2O4 gas inside this piston cylinder. Give me a gee whiz value for this volume. V is about how much? How many liters? 1 mole, this gas, taking it to show a behavior that's describable by PV equals nRT. The equation of state for the ideal gas. Give me a gee whiz volume. You did this gas law stuff in 2045. Now let's put it to use. I'm listening. I heard a value of 22.4. That's too small. Because 22.4 is the molar volume of an ideal gas at what temperature? What temperature? 273 K, 0 centigrade. But now we're considering operating at NLC. I mean, I don't want to stand around and do any work at 0 centigrade. I don't like that. I'd be too cold. Wouldn't you be too cold? Here I've got an ice water slush, 0 centigrade in there. You want to dive in there? In the wintertime, some of these people do this in places like Pennsylvania and Ohio and Michigan. I think these people are crazy. But if they like it, that's okay. The Polar Bear Club. Woo-hoo! Go away. To me, snow belongs in your backyard, not mine, and on postcards and in newsreels. I don't want any part of snow again in my life. I don't want it. My wife wants me to take her someplace where it's snowing. This runs chills up and down my spine for obvious reasons. Of course I'll give in because she's a sweetheart. But I don't want any part of that damn snow. Actually, it wasn't snow that gave me a lot of problems in Toledo, Ohio. It's this driving, freezing sleet. You can put on 8 jackets. I don't care. It still makes you cold. Anyway, the hell with that. Back to this. This is at 298 K. So if you take 22.4 liters, which is the ideal molar volume of a gas, ideal gas, at 0 centigrade, and multiply it by 298 K over 273 K, then you'll get the volume, which is about 25 liters. So for starters, if we're going to do this, we need one hell of a big piston cylinder gadget. Now I got a question about this reaction. First of all, can I say for sure this reaction is exo or endo? I'm listening. I heard a vote for endo. How many endo votes? Remember, I'm asking if you can say for sure. Can you say for sure whether or not this reaction is exo or endo? All right. I'll tell you, yes, you can say for sure. And endo is wrong. You see that reaction? It involves taking 2 moles of NO2 and putting them together to make 1 mole of N2O4. That reaction is nothing but bond forming. You agree? It's strictly bond forming, so this has got to be exo. Now let me tell you something else. Directive, I want you to write Lewis structures for each of these molecules. But this is a brown gas. We'll talk about why after you consider the Lewis structure. This gas is colorless. So given that this reaction is exo, if I have this reaction system, like I do right here in this flask. In this flask, I'm telling you right here now, I have a mix of NO2 gas, which is brown, and N2O4 gas, which is colorless. If I take the contents of this flask and heat, am I going to shove that reaction as written, or am I going to shove it in the opposite direction? What's going to happen? By adding heat, do I increase the tendency for bonds to form, or do I increase the tendency for bonds to break? Bonds break. Well, breaking is going this way. So if I had heat to this system, should the brown color get more intense or less intense? More intense. Let's take a look. I have set this demonstration up, and we're just going to have 1 minute time to talk about it. Here I have that flask at 68 degrees centigrade. Here I have the same flask, well, same contents, at 0 centigrade. See any difference in intensities? Here's the cold one, much more colorless. Here's the hot one, much more brown, because in this one, the N2O4 concentration is a good deal higher than it is in this one. And in this one, room temperature, the N2O4 concentration is higher than it is in here, but in here the N2O4 concentration, the colorless stuff, is lower than it is in here. Pick it up from this point next time. Write these Lewis structures before you show up for our next chat.